Okay, good morning, everybody. We shall start the morning session, and the first speaker is Takafumi Tomita, and he's from Institute of Molecular Science, and as we learned, also from Sokendai. So his talk is on controlling ultrafast Rydberg dynamics with ultracold atoms in optical tweezers.
Okay, thank you for the introduction. Good morning, everyone. I'm Takafumi Tomita from Institute for Molecular Science. And first of all, I'd like to thank the organizers for giving me a chance to talk at this wonderful conference. And today I'm going to talk about how to make interaction between two distant neutral atoms and how to make it faster. Okay. So and I'm from this Aichi prefecture, Okazaki city, which is like the IMS is placed at this place. And I'm from a research group, Kenji Omori's group. And my research topic is experimental research on quantum computing and quantum simulation using cold atom. And personally, in my PhD course, I was working on still this cold atom experiment, especially making open quantum many-body system. Actually, yesterday, Halta-Saxon introduced the quantum platform is really ideal, isolated quantum system. But at that time, I was opening, I was trying to make open quantum system. Yeah.
You're going beyond.
Yes. Yeah. And then after that, I moved on. I moved to IMS, and then again I closed the system as to make ideal isolated quantum system. And yes, especially working on Rydberg physics. And also, I'm working with a theorist. There's a proposal using cold atom to realize Jelinsky-Moria interaction, for example. And this collaboration work with Kunimi-san and also Katsura-san and Kato-san. Especially this work is presented in this poster session. So if you're interested, you can visit the Kunimi-san's poster. And also, I give a lecture online. There's a lecture video on YouTube on the cold atom experiment. So if you're interested in the detail of the experiment, you can visit the YouTube video of this quantum education program in this Japanese. Okay, so as you heard, there are plenty of experiments using cold atom, and there are a variety of experiments for quantum simulation, or for quantum manipulated physics, for example, investigating quantum phase transition, or say using Fermi-Hubbard system, they investigate a phase diagram, or say around like steady state, which is predicted to the connection to high thesis for conductivity. And also, thanks to this state-of-the-art technique called the quantum gas microscope, you can identify each spin state for each atom, and then you can calculate, for example, correlation function directly. And this is a good platform for non-equilibrium dynamics because this is really ideal isolated quantum system. And not only for such kind of itinerant system like Hubbard physics, people investigate the spin system, and there are several experiments on Ising model or Heisenberg system. And also recently, the investigation for realizing quantum computer is really a hot topic in this field. And my talk is the kind of key element or key ingredients to realize a many-body system, which is just interaction between two atoms. And my talk is basically atomic physics, so it's not many-body physics or non-equilibrium dynamics, but I think I hope you can enjoy it. The topic is how to make ground-point interaction between two neutral atoms, and then fastest way to interact them with each other. Okay, so and also I feel that it's a good chance to introduce what is the cold atom experiment itself, because I think you often heard cold atom platform is a good system for investigating many physics, but I feel that it's not. You don't have many chance to know what the experiment is itself. And also the next talk is also quantum cold atom experiment. So I just want to briefly introduce cold atom experiments. So the system is like this. You can find lots of, say, mirror or lens to guide the laser to the atoms, and atoms are placed at this vacuum chamber where there's no air. All the air is evacuated, and then inside you can introduce a specific atomic species like rubidium. And this is the photo that I took in our lab, and this is the trapped rubidium gas. And a little bit more detail. So how to make this kind of cold rubidium gas? There are actually so this is the photo of the individual rubidium atom taken by a camera, CCD camera, and you can make this kind of artificial quantum system. So how do you make this kind of cold rubidium gas? So there are several steps. Step one is laser cooling. So just three-step explanation. So suppose we have an atom which is going to this direction, and then this atom has an internal degree of freedom, for example, ground state or the electronic state and excited state. And then you can shine the laser from opposite direction, and whose frequency is tuned to the resonant frequency for this transition. And then atom will absorb this one of the photon and then excite to excited state. And the important thing is that photon has a momentum. So momentum is transferred to the atom, and then atom will decelerate. This is also called radiation pressure. And at some point, the atom will emit the photon, and it's called spontaneous emission, and then go back to the original state, this state, and then again absorb another photon. And then repeat this procedure again and again. And actually, this spontaneous emission process also makes another momentum kick. But since this momentum direction is random, so through this process, the vector of sum of this momentum kick is cancelled out. In the end, you can decelerate the speed of the atom at a specific direction. Now, this is a schematic. Maybe you can imagine this guy will decelerate. And this is called laser cooling. It's a Nobel Prize technique. And the temperature original temperature is 300 Kelvin, room temperature. And after this laser cooling, the temperature goes to tens of microkelvin in the case of rubidium, which correspond to the speed of atoms starting from 100 meters per second. It's almost the same as speed of sound. To go to 10 centimeters per second, it's like this speed. Okay, so now you cool down the atom motion of the atom, then you can actually use laser to trap single atom one by one. There's a force from laser, and then this tiny force is enough to trap atom. So to trap the atom, we again shine laser to the atom, and then in this case we focus the laser using a lens. And the laser frequency is off detuned from the resonant frequency. And at the focal position, if there's an atom, then the atom feel oscillating electric field. And this electric field will polarize the atom cloud. And then this polarized atom has a dipole. And this dipole and electric field, again, interact with each other, like this U equal minus D dot E. And then the D dipole is proportional to the electric field. So in the end, the interaction strength is proportional to the minus E squared, electric field square intensity. So in the end, if you have this kind of intensity profile of the laser, then the atom feel this kind of negative potential proportional to the intensity profile. Then you can trap an atom. So if you tightly focus the beam to micrometer region, then in the end, you can just trap a single atom, and this is called an optical tweezer. And optical tweezer technique is originally invented for research for biological systems, but now that you can use this technique to atomic system also. And you can make array of this optical tweezer. This is called optical tweezer array, and you can draw any kind of dots of atom. Like I wrote this laser photo inspired by yesterday's Derek talk, and yeah, this is the way to make an arbitrary shape of array of the atoms.
So how do you separate the atoms? There are many atoms initially, right? So
yeah, so So first you can make this kind of cloud of atom, which contains, say, 100,000 of atoms. And then we superimpose, overlap this optical tweezer light. Then spontaneously atom drop to this kind of pocket. But sometimes atom drop, two atoms drop simultaneously. But during this, say, the center you shine this cooling light, and then this cooling light introduces kind of inelastic collision. It is called light-assisted collision. And then in the end, if two atoms try to enter the same potential, then there's inelastic collision, and then two of them, two atoms will disappear. If you have three, then two of them will disappear, one remains. In the end, you can get, you can trap one atom or just vacancy, no atom. And I don't explain the detail, but after that, after trapping atom, there's a lot of vacancy site, and you can reassemble the other optical tweezer. It is called the atom by atom reassembly. Then you can make this kind of array.
I see. Thank you.
So is there some remaining micromotion in these traps, or are they really?
Yes. This is a really good point, and I will introduce such kind of micromotion later. So this quantum simulation for spin system or quantum computation experiment is based on this optical tweezer technique. The question is, how do you introduce interaction between two neutral atoms? This is the topic I want to talk today. This is actually not trivial because this is neutral atom. There's no Coulomb force, and also the distance between two optical tweezers is few micron. And then on the other hand, the size of the atom is less than 1 nanometer. So it's let's say 10,000 times different. For example, if my height is 1 meter, and then I want to talk to 10 kilometer as a person who is placed at 10 kilometer away, and it's not easy. The trick is that actually there's a technique to expand your body size, and once you expand the body size, then you can talk to other person. This kind of gigantic atom is called Rydberg atom, and this state is called Rydberg state. And then you can make electric dipole interaction. A little bit more detail of Rydberg atom. So Rydberg atom is a gigantic atom whose outermost electron is excited to release a large orbit corresponding to the high principal quantum number n, around few tens of 40, 50, 60 to 100. And then this radius or diameter of this atom or orbit is order of 100 nanometer. And then thanks to this large orbit, this atom has large dipole moment, and then there's electric dipole interaction. And essentially the Hamiltonian is like this. Actually, this is a little bit more complicated, but I just simplified it. And then you can get this 1 over r cubed scaling interaction. What is good is that if you want to if you want to make interaction between this atom and this atom, then you can excite these two atoms and then make interaction. If you don't want to make interaction, then you de-excite it.
But this is not a hydrogen atom, so there are a bunch of electrons.
Yes, there are a bunch of electrons, but essentially this gigantic Rydberg atom is almost same almost same profile as just hydrogen, because
Okay, so you mean only one electron is in this, and the other guys are still.
yeah, and it's effectively just a +1 charge. Yeah.
If they're so excited, what's their lifetime? Wouldn't they just?
Yeah, this is also a very good point. The answer is the order of 100 microsecond, and this is the kind of limitation of the experiment. And this is I also want to comment on this later.
Excuse me. So in this Rydberg state, they have dipole.
Yeah. So actually, I explain a little bit, let's say, in a little bit simplified manner. Actually, there's no eternal dipole because say electron doesn't have doesn't place up the specific direction.
Yeah, I think so.
Yeah. So in the end, what you get is not directly type of interaction, but second order interaction called van der Waals interaction. I also introduced this later, but in the end, what you get is one of our sixth interaction.
I see. So strictly speaking, the interaction is different from that.
Yeah,
I see.
I will introduce how to get this direction.
I see.
How to overcome this accuracy. Okay, and also, yes, I want to mention that you can control the interaction strength, of course, by changing the interatomic distance, and also by choosing specific Rydberg state. If you have a higher n, then you have a stronger interaction strength. And I pick up one of the example, n equal 40, then this coefficient C3 is 1 gigahertz micrometer cube, which means that if you bring two atoms at 1 micrometer separation, then you get 1 gigahertz interaction strength. In other words, the interaction timescale is nanosecond. It is actually quite strong in our community. So usually we have a megahertz interaction or even a kilohertz interaction. So it's quite, let's say, useful.
What is J?
J is the interaction strength derived from this, for say the expectation value for the. Yeah, so this is about this van der Waals interaction. So actually, there's several barriers to not realize just direct dipole interaction, and one is this dipole-dipole to van der Waals. So actually, in classical picture, this dipole-dipole interaction is like this two dipole will feel electric field with each other. But in quantum picture, two atoms throw and catch virtual photon with each other. And what happened in this dynamics is, for example, if you bring two atoms at a specific Rydberg state, for example, in d orbital or specific n, then one atom goes to another Rydberg state by this dipole interaction. One atom goes to this state, another atom goes to this state, and just throw and catch virtual photon. If you describe this in a pure state energy, so you can consider this is initial state R, this is the final state R prime, R double prime. Then most of the case, this initial state and final state is not the same energy. So there is energy gap delta E. Then what happens is not just, let's see, this dynamics actually not happens, but there's second order perturbation, and in the end you have an energy shift of this initial state, and this is called van der Waals interaction, second order interaction, and this is interaction strength divided square divided by delta E. So this should be J maybe, and in the end you get the 1/6 interaction. And more the distance between two atoms is not 1 micron, but maybe few micron in most of the case. In the end, this R value is not so small. What you get in reality is most of the case van der Waals interaction order of 1 to 10 megahertz. So it's different from just nanosecond interaction or gigahertz interaction.
I'm confused. So you have this out to the sixth interaction. You had out to the cube in the previous slide.
Yeah.
I'm sorry. So this is the interaction you have.
This is the interaction in most of the case, and today's talk is how to overcome this perturbation, perturbate the region, and how to realize direct. Because my goal is to make interaction faster as fast as possible.
Okay, thank you.
Yeah, so and then the final barrier is how to excite the atom to Rydberg state. So to introduce this, I describe the time scale of the Rydberg physics, and to answer the question of the lifetime. So lifetime is around here. So Rydberg state is not a metastable state, but there's finite lifetime, which is 100 microseconds. And on the other hand, the shortest time scale is determined by the binding energy of the outermost electron. If you try to shape or if you try to make dynamics in the scale of picosecond, then in the end, outermost electron goes to the continuous. And also another limit is state splitting. If you want to specify a specific Rydberg state, then your dynamics should be slower than the inverse of the energy separation, which is 10 picosecond. And the interaction is somewhere here. And in conventional experiment, people use continuous wave laser. It is like this kind of laser pointer, like laser. You can keep shining laser, and this is just continuous oscillating electric field. And if you use this continuous wave laser, then the time scale of the excitation is order of microsecond, just simply limited by the strength of the electric field. And then in the end, if you combine this interaction and this excitation scheme, then all the total time scale of the physics is limited by this excitation time scale, which is a microsecond order. And what I want to introduce, or what we did in our research, is to overcome this limit and how to say realize this bare interaction by using ultrafast picosecond pulse laser for excitation. So the time scale of this excitation is faster than the interaction time scale. So if you combine this and this, then the time scale of the physics is not limited by the excitation time scale, but just simply limited by this interaction time scale. So we hope that we can observe interaction more, let's say, directly. And this is called a speed limit control because just physics is not limited by the excitation scheme, but limited by the interaction. And why do we want to make ultra fast, or say, why do we want to make it faster? The reason is I want to stay farther away from this finite Rydberg lifetime. So this time scale is already fast 3 or 3 order faster than the lifetime, but still you have some chance to decay back to the ground state. If you bring this to this level, then it's a little more safer, or it's more closed, isolated quantum system. And also you can overcome noisy environment. For example, in the experiment, this is a little bit experimental detail, but the fluctuating electric field or magnetic field, whose time scale is order of microsecond or say nanosecond, and you want to avoid this kind of say effect, and you want to finish all the experiment faster than the noise time scale. And also, atom can move, and you want to avoid such kind of effect by finishing all the experiments faster than this time scale. Okay, so this is our outline already. I already spent maybe some 20 minutes.
So may I ask? I was expecting you were going to mention that your computer, your quantum computer, will be faster this way. Is that so, or?
Yes, so it's yes. So in the end, I want to introduce the application to the quantum computer, and we believe that for the two-qubit gate will be faster than the conventional two-qubit gate.
Thanks.
Okay, so I already introduced what is cold atom platform and what is long-range interaction between two atoms, and then from now I want to introduce our research, ultra-fast excitation by picosecond laser, and then ultra-fast Rydberg interaction. And I want to finish by mentioning outlook. So this is our atomic array, and you can find the dot, and this dot are the fluorescence from the atoms, rubidium atom, and the optical tweezer is made by this state-of-the-art optical element called spatial light modulator. You can modulate the surface wavefront of the laser, then you can make arbitrary shape of the focused pattern. And thanks to this technology, and also thanks to the high resolution objective lens, then you can make this kind of dot pair of atoms, array of pair of atoms, and you can tune the distance from distance between two atoms. And the shortest distance is 1.2 micron. This is actually the record. This level of this short distance that we never achieved before this experiment. And okay, so now you load two atoms at this pair potential, and still atom is moving because atoms are loaded from thermal gas, and the temperature is 50 microkelvin, which corresponds to the fluctuation of the position of order of 100 nanometer. It means that it's a little bit problematic because the interaction is proportional to the 1/r cube. And then if the interatomic distance is fluctuating, then the interaction also will fluctuate. And to reduce this kind of fluctuation, we apply the further, there's another cooling technique called Raman cyclone cooling. I don't explain the detail of the experiment, but essentially you can remove the quantum of motion one by one by applying the laser whose frequency is tuned to the difference of the quantum motion quantum. And then you can reduce the atomic motion to the motional ground state of the atom. This is exactly the same as what you learned in the quantum mechanics lecture. This is the motional ground state of the harmonic potential. It's almost harmonic potential. In the end, the fluctuation is reduced to a few tens of nanometer, which is of the quantum fluctuation level. Then let's go to the excitation part. So I told you that conventionally people use continuous wave laser excitation, and then now we use picosecond pulse laser excitation. And there is this bit of difference between this continuous wave excitation and the pulse laser excitation. The difference is that in the case of the continuous wave laser excitation, so first, this is the ground state of the rubidium. This is the excited Rydberg state of the rubidium. We chose 43D. And then the transition energy or the frequency is the UV range from this to this. So it's experimentally it's a bit difficult to make UV light with enough power. So often, most of the case, people use 2-photon excitation through this intermediate state. And this intermediate state lifetime is too short to stay here. So you put the detuning or energy mismatch intentionally, and then shine these two lasers simultaneously. In the end, the coupling strength between the ground state and Rydberg state is order of megahertz. In other words, the excitation time scale is microsecond. On the other hand, this picosecond pulse laser excitation, this intermediate state is no longer short lifetime, but more like stable, because from the point of view of picosecond pulse laser, the lifetime of nanosecond is really long. Just you shine one first laser, and then you shine another laser. Then you can get excited Rydberg excited state. So this is the experimental result of the pulse laser excitation from ground state to intermediate state. You can see this kind of coherent oscillation is called a Rabi oscillation. You can choose specific pulse area, timing, and energy of the pulse, and you can coherently excite atom to intermediate state. And then after that, you shine another light laser from to excite from intermediate state to Rydberg state, and you can get also another oscillation. In this case, actually, this you can choose the specific time and the pulse energy to get this excitation, excited state. But in this case, the excitation is not perfectly coherent. The problem in our experiment is pulse-to-pulse energy fluctuation, and then this is solved after this experiment. So I will mention this at the end of the talk. Anyway, so in total, excitation time is few tenths of picosecond. So you can almost immediately excite atom to Rydberg state.
Excuse me. So pulse laser contain the multiple frequencies, not a single current. So, but is that better for this kind of process for Rabi oscillation?
So this is a really good point. So you have to carefully select the bandwidth of the pulse laser. Bandwidth is the inverse of the time duration of the pulse. For example, in our case, picosecond or tenth of picosecond pulse laser has 100 gigahertz bandwidth, and this should be smaller than the Rydberg state separation. And so if you cannot shine, let's say, femtosecond laser, because femtosecond has too large bandwidth.
I see. Got it. Yeah, thank you.
Okay.
One question. Yeah. So this whole thing with the gap and the time of the laser, that takes like 30-40 picoseconds total.
Yes.
That's the time scale we are thinking about.
Exactly. All right. So now you can excite the atom to Rydberg state. Let's see the interaction between Rydberg. So again, I show the time scale of this Rydberg physics because I want to mention one thing, especially for people who already know about the Rydberg physics. Conversely, I said that conversely people use continuous wave excitation, and then the time scale is limited by this excitation time scale. And actually, what happened in this excitation scheme is that you can excite, for example, suppose we have two atoms, and you can excite one of the atoms to Rydberg state by just carefully tune the laser frequency to this excitation resonance frequency. But if you try to add the atom to Rydberg state, then the final state, RR, Rydberg, has an interaction energy shift. And this interaction energy shift is so large that you cannot, so this laser is no longer resonant to this second excitation. In the end, you cannot simultaneously excite both two atoms to Rydberg state. It is called Rydberg blockade. And this is the conventional phenomenon happening in this experiment. But in this ultrafast excitation, this blockade never happens because the one explanation is that this bandwidth is larger than the interaction strength. So it's in this ultrafast excitation, you cannot you can ignore this interaction energy shift, but you can just shine the laser to directly excite from ground through ground Rydberg and Rydberg. Another explanation is that the ultrafast excitation is too fast or so fast that the atom does not realize another atom here is excited. So atoms are excited, and then I realize, oh, you are excited. Okay, let's do like that. So what the message is that you can simultaneously excite all the atoms to Rydberg state without carrying the Rydberg blockade. This is a special physics in this ultrafast excitation. So in our experiment, we excite, for example, two atoms to a specific Rydberg atom. I chose 43D state. What happened under this dipole-dipole interaction is that, again, so this virtual photon from catch, one atom goes to another Rydberg state, called 41F in this case. Another atom goes to 45P state. And then actually, we carefully chose this initial state so that this energy difference and this energy difference is equal, almost equal. In this pair energy state picture, the initial pair state 43D is on resonance to another pair state 45P 41F. In this case, there's no second order perturbation, but you can realize fast order dipole-dipole interaction. And this kind of accidental resonance exists in this Rydberg atom, and we just chose this 43D state because of this to realize this physics. And this resonance is called Forster resonance. And now we have two resonance states, and then we have coupling. Then what happens is oscillation between these two pair states. And this oscillation is called Forster oscillation. And the dynamics is described like this. So initial state is D state, for example, and then final state is PF state. Actually, this is symmetrized version of PF, P plus FP, PF type tilt. And then the dynamics is simply like Kavli oscillation, cosine JJ minus I sine PF. And this is what we expect to observe.
How good is this resonance?
Okay, so there is still a little bit of a mismatch of the energy. It's order of megahertz, and compared with this interaction strength can be order of gigahertz. So it's almost negligible. So we can say safely it's resonant condition. Okay. Let's observe this oscillation. So the experimental procedure is as follows. First, we excite both two atoms to excited Rydberg state using this picosecond pulse excitation, and then just wait for a while. In our experiment, 6.5 nanosecond. And during that, atom just automatically, spontaneously make interaction. One atom goes to another state, another atom goes to another state, and then after that, maybe just sometimes go back to the initial state, 43 equals 3. To detect the population in this 43D state, we can shine de-excitation pulse to detect the population of this state. So this is the experimental results. It's a little bit complicated. I want to explain one by one. So first, in our experiment, we fix the time of this interaction, but instead we tune the distance between two atoms. This is the parameter. And then, for example, if you put two atoms at the 5 micrometer distance, 4.9 micrometer distance, then this distance is too far to make interaction. In the end, the population in this state is relatively high. If you bring two atoms, this is another experiment. If you bring two atoms to 3 microseconds here, then in this interaction strength and in this time scale, then two atoms goes to 41 F state and 45 P state. In the end, the population in this state drops. If you bring two atoms closer, this is another experiment. If you bring two atoms 2.4 micrometer separation, then this interaction strength is it corresponds to 2 pi oscillation or 1 turn oscillation. In the end, the d equation again goes up. If you bring two atoms even more closer to make higher interaction strength, then there's 1.5 turn oscillation, 3 pi oscillation, and then the population drops, and so on and so on. And to make it a little bit more clear, we can replot this result as a function of interaction strength times time. And then you can see oscillation. This is nothing else than this ultrafast Foster oscillation. And this is the actually first time observation of the interaction between two distant Rydberg atoms in this nanosecond time scale. And this is the speed limit control of the interaction between two atoms. And I was happy because this is covered on the front page of the Nature Photonics. The reason why I said I was happy, but is I made this graphic. I like this 3D graphic drawing, and this is covered Nature Photonics. Okay, a little bit more quantitative analysis. So first, we found that this interactions timescale or oscillation period is perfectly mapped to the C3 coefficient calculated ab initio calculation. And but you can see that there's damping. It's not perfectly pure coherent oscillation. The reason is what we identify is that one is that still there's a quantum uncertainty of the position, which means that the interaction strength is still fluctuating in quantum level. And this gives you the first little bit of drop. And another reason is that actually I said that there's this pair-to-pair interaction, but there's actually this off-resonant van der Waals interaction a little bit, and this makes it a little bit complicated. And then there's another drop. But then to answer your question, yeah, so we can apply this technique to a two-qubit gate, for example. And then what we demonstrated is that so we prepare this ground this state and this state, superposition of this state and this state, and we prepare two atoms. And then based on this equation, you can find that at JT equal pi, so here, the state goes back to DD state because cosine DD state, and then this part disappear, but this cosine pi is not 1 but -1, so DD goes to minus DD. This is what happened in this Rabi oscillation. And if you prepare this kind of superposition, then in the end, the final state is plus, 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 minus. And this is entangled state. And I don't have, let's say, enough time to explain the detail of the what we did, but we performed kind of, say, Ramsey type of experiment to detect the phase factor of this DD state. And then we realized, we found that actually we could realize this kind of entangled state. And this is a 2-order factor than the conventional 2-qubit gate based on Rydberg block gate. And I know this is still the fidelity or say precision is not very much good, but we believe that this is another way to make a control Z gate in quantum computer.
So if it's the R to the cube, what about the neighboring, nearest neighbor, nearest, etc.?
Yeah, so yes, if you make regular array, then you have to consider next nearest, but now we prepare a pair, just a orange pair.
Next pair.
Yes. All right. So I said that this is not still perfect. We are now currently working on how to improve this physics or say dynamics. One improvement is laser excitation part. I said that there's a pulse to pulse, a shot to shot energy fluctuation on the pulse, and this limits the excitation probability to the Rydberg state. And recently we identified the source of the this noise or shot to shot fluctuation. This is completely experimental detail, but we were using current commercial laser source, but we found that one of the commercial laser source had a bit of problem to make a wavelength conversion procedure, and then we decided to make our own homemade pulse laser system, frequency conversion system, and then thanks to the technique called injection seeding. This is the technique to stabilize the shot-to-shot fluctuation. Then we could reduce the shot-to-shot energy fluctuation, and then we improve the excitation probability. And this is one improvement. Another improvement is how to reduce the position fluctuation even further. I explained that we already applied Raman sideband cooling to reduce the motional state to quantum ground state of the harmonic potential. But there's a way to go beyond it. The way is to make squeezed state, motional squeezed state. So this is the not the shortest, the smallest or narrowest reduce of the wave function, but if you can make this squeezed state at this timing, the position spread is narrower than the original this wave function. So the way to make it is first we prepare atom at the in the tweezer. There's a kind of harmonic potential, and then at some point, we turn off this potential. Then atom wave function spontaneously start to spread. Then after some time, we again turn on the potential. Then atom wave function start to move like this. And this figure or graph is the description in phase space with X and P space. And once you turn off the potential, then the this kind of regular distribution start to stretch in this direction. And then once you turn on again, then this stretched distribution start to rotate like this. And then at specific timing, you can get narrowing. But in other timing, you get the spread, and in other words, momentum squeeze state. And this is the experiment to see how much the wave function is stretched, and you can say make a release and recapture like measurement where you can again turn off the trap, and then after some time you trip again the atom, and then how much atom are remained, and then which correspond to the momentum or speed of the atom in the tweezer. And then this position squeeze state, then the momentum spread is too large, and then atom quickly disappear, and then there's a sudden drop of the remaining probability. This means that there's a position squeezing.
This is an ultra-cold regime, so this is not thermal fluctuation, but this is quantum fluctuation.
Right. So first we remove thermal fluctuation, and then apply this squeeze procedure.
And is the wave function still spherically symmetric in this case?
Okay, so this is a good point. So it depends on the shape of the tweezer.
Yes.
If the tweezer potential is asymmetric, like for example elliptical and horizontal harmonic potential, the vertical is not the same, then there's strange. But we carefully form the tweezer shape as circle as possible. So we have a symmetric squeeze state.
Excuse me. So to combine this squeeze state with your previously mentioned such a two-qubit gate, you need to, how say, carefully choose the timing of the pulse excitation also. Yeah.
Yes, exactly. So yes, so we have to carefully choose the specific timing to apply this two-qubit interaction. And actually, the time scale of this squeezing is determined by the trapping frequency, which is way slower than this ultrafast physics. For example, the order of microsecond. And you can start and finish all the ultrafast experiment at exactly this timing.
I see.
And you can identify this timing really easily. You can monitor or you can measure the oscillation period, and you can precisely determine the time to shine pulse laser.
I see.
So actually, we don't have data after this. We don't have data of the ultrafast interaction after this improvement, but we hope that we will soon get a better result. Okay. So at the end of the talk, I want to introduce a little bit different direction. Not only for this atom by atom or two-body interaction, but we can extend this ultrafast physics to many-body physics. And we have an optical lattice system, not optical tweezer system, where you have a little bit shorter interatomic separation, and then you have a larger number of atoms. And then what we found during the experiment is that since you excite all the atoms to Rydberg state, and the atom will make interaction with each other, atom will force if you have this van der Waals regime, if you change the internal Rydberg state, then you can make a strong force between two atoms. And there's no force between ground state, or ground state, Rydberg state, or Rydberg and ground state. But only with the Rydberg state, there's a strong force. And this is kind of a spin motion coupling. And spin means that the ground state and Rydberg state is the same meaning as this two-level system, and spin state. We say spin state as this meaning. And then we found that there's actually spin motion coupling, and this is a little bit indirect observation of the existence of the spin motion coupling. But in this many-body system, we applied a similar kind of experiment as two-body experiment that I explained before. We applied the Ramsey kind of measurements to see the coherence or amount of entanglement, and then we realized that it's the behavior does not explain if you don't consider the spin motion coupling. And during this, in this paper, we propose that we can use this spin motion interaction more in a more tunable way. The technique is what we call ultrafast stroboscopic Rydberg interaction. So we repeatedly excite the atom to Rydberg state to make force, and then once you make force, then atom feel momentum kick, and then bring back to ground state, and then wait for a while, and then again shine another pulse, make momentum kick, and then bring back to ground state. And if you repeat, then it's kind of reciprocal like engineering. In the end, effectively, you can make a tunable strength of the spin motion coupling, or say long range interaction between two ground atoms. And this is what we propose. And then we believe that we can explore a little bit new direction of the many-body physics using this stroboscopic Rydberg interaction. Okay, so it's almost time. Yeah, so to summarize, I introduced cold atom platform or cold atom experiment, and introduced long-range interaction between neutral atom, and then introduced a little bit new technique based on picosecond pulse laser to make interaction faster than the conventional way, and some application on force motion squeezing and spin motion coupling. And this is done in Kenji Mori group here, and these are the main contributor of this experiment. And I'd like to finish my talk. Thank you very much.
Okay, questions?
Yeah, thank you very much. And let me ask a rude trivial question that everybody's interested in. So I guess you guys are competing with the Harvard group. Building a computer based on this.
Okay,
Atoms.
yeah,
Yes, yes.
yeah.
But that's what Kenji Omori said to me.
Right.
Now, then you have this you realize this 2-qubit gates, but in order to do that, you have to bring these two atoms very, very close to each other. So you can just manipulate them this. If you're not really quantum compute, you have to sort of bring them together and then separate and bring it. So is it kind of possible or how difficult? What is the perspective?
So okay, so so first you're right. You have to bring two atoms to the close distance and then make this gate and then bring it back. And this is almost the same procedure as what the Harvard group is doing, and there's no difference.
But you're closer than you bring them closer than they do, right?
Yeah. So okay. So in this sense, so for quantum computation, we should care the balance between the fidelity and also the I would say how easy you can do this experiment. And what I described here is kind of the fastest limit of the physics. And I'm not saying that we should do this 2-qubit gate in this time regime, but maybe we should slow down, still using this pulse laser to make it more safer, or I say to improve the fidelity. Because if you bring two atoms closer, then you have a more effect on the this position fluctuation.
So one more question. So you have this picture of pairs of atoms.
Yes.
Can you bring all them together at the same time, or you tune each of them?
Okay, so we could successfully make this pair of atom with 1 point down to 1.2 micrometer, and I said this is well. We found that it's a little bit difficult to make regular array with 1.2 micrometer separation. If you bring many tweezers at this almost the same position, then the tail of the electric field or say light start to interfere with each other and then make it a bit messy. But still, you can make, for example, 2 micrometer separation or say 2.5 micrometer separation. And then one way is just make this small regular array and then explore many body physics.
Thank you.
Questions. So I have 2 questions. Thanks for the great talk. So first of all, this long-range interaction between atoms. Is it possible to engineer specific long-range force that I want? For example, 1 divided by distance square or 1 divided by distance. Is it possible? Okay. So the answer is, as far as I know, no. So it's limited by this type of level physics. And 1/cube and 1/6. Actually, I've heard that in trapped ion people, they manipulate the power of the interaction, I mean the distance. I think they can make some arbitrary number between 3 to 6 or something like that. But I don't actually. I'm not familiar with this. I see. So below 3 is difficult. Okay. And also in practice, suppose I want to model a spin chain. How many spins can I model on this Rydberg array? Model means realizing experimentally. So I mean, for example, for spin chain, I have certain lengths, which means I have say 100 spins interacting with each other. And I guess in real experiments, you can do like control finite amount of atoms on the ring. Yeah. So how many atoms in practice can we control? Okay, so the answer is maybe order of few tens, maybe close to 100. Okay. Yes, it's not like 1,000 if you make 1D chain. So currently in the community, people are try to make the array bigger and bigger. The largest array size is in 2-dimensionally 10,000, which means that 100, 100. So in 1 dimension, 100 is maybe a good number. I see. Thank you.
Nice.
Yeah.
Thanks for the very results. So a question about the force equation, force resonance without observation. So we know from other people that if you do the full CAD engineering for excitation, you can extend blockades or radius, or you can reduce the Rydberg blockades, for instance. Have you ever thought about this full CAD engineering for your ultrafast machine?
Okay, engineering to extend the Rydberg blockade radius.
Or sometimes they can introduce the anti-blockades using this.
Okay. So honestly, I've never seriously considered this kind of application on this ultrafast experiment.
I'm just curious, and you can, what is the fastest off resonance effects
Okay.
by doing this okay.
I see. Thank you.
Thanks.
More these types of questions see in the context of quantum, like using it in a quantum computer. So I guess there's three small questions. The first is the current speed in the Nature Photonics paper is 40 picoseconds plus the 6.5 nanosecond interaction time. What's the fidelity you get for that? And the second question is, once you have all these improvements, what fidelities do you expect, and how long will it take, including, I guess, the squeezing time? And then the third question is, sorry, is
You can't remember.
do you expect the gates to be the speed limiting ingredient in a quantum computation when you also have all this moving around with atoms?
Okay, so maybe I'll ask the question again. The first question is the time to perform this gate, right? So yes, you're right. So it's few tens of picosecond, maybe 40 picosecond plus 6.5 nanosecond. This is correct. So and then if you want to apply this technique to say serious quantum computation, then not only this kind of improvement, you need a little bit more work, hard work to improve the fidelity. For example, one thing I didn't mention is that how to remove the derivative effect of the Van der Waals shift, which from this state and this state, and this also affects the reduction of the fidelity. And there's a way to shift this state and this state by applying, for example, microwave or static electric field, and then make a Stark shift to tune the energy this more farther away to make it more pure to the pair by pair interaction. And also if the time scale, including the for example squeezing, in the end the time will be similar to the conventional time scale of the 2-qubit gate in collateral experiment. The point is that I don't want to say that this is the way to make the 2-qubit gate faster. But the first motivation is to stay away from the finite lifetime of the Rydberg state. As you know, so this ultimately determines the fidelity of the Rydberg interaction with Rydberg 2-qubit gate, and then this conventional gate also suffer from this finite lifetime. If you can reduce time to stay in this Rydberg state, then in the end you can avoid this effect. This is the original motivation. So in the end, we don't very much care about the total time of the 2-qubit gate. It's fine to have a microsecond, but just I want to reduce the time to spend in Rydberg state. And yes, sorry, this
No, I think actually answered my question, just how it would be used in the whole experiment. I was just wondering about the fidelities.
Yes, yeah. So so we said that it's say long-term project. I would not say that soon we will beat the conventional 2-qubit gate in quantum. It's really nice. Currently, they have a 99.5% fidelity in 2-qubit conventional blockade gate. It's difficult. We have to reduce we have to improve the fidelity one by one, but just scientifically, yeah, it's interesting.
Okay, I had one big question, if I may. So, if we are thinking of building an array out of this, think of a one-dimensional array. How close can you bring this array atoms so that this oscillations or your entanglement is not going to be significantly affected? Because you mentioned that you're doing two atoms.
Yeah.
And apparently presence of other atoms nearby is going to affect this process, right?
Right.
So in terms of making an array, how serious a constraint is that?
So if you don't consider the pair by pair configuration, if you want to make say regular array with the same separation, then you always suffer from other not depends on the say separation, but just a ratio between neighboring side and next neighboring side.
Okay, so that can be tuned, I guess, right?
That can be tuned, yes.
Make this distance large and
Large, but still you cannot avoid the effect from next neighboring.
And this also affects the entanglement between this dd going to minus dd thing that you showed. That entanglement is affected by this process.
So what we believe is that if you make 1D regular array, and then if you apply just global this laser, then you can simultaneously apply this kind of CZ gate. You can, it's same as two-qubit gate as this pair and this pair, this pair, this pair. But still, you cannot avoid this. But it's, I feel it's interesting in the field of many physics. Yes.
Please. Eventually, you want to do quantum error correction. So you have to invent the physical word. So what is the time scale and what is the process?
Okay, yeah. So it's completely actually out of the my talk, but over on the computer. And many people ask a question about the time scale of the measurement. Actually, the whole time scale of this quantum quantum computation in quantum transform is the measurement. The measurement is order of millisecond, and the gate speed is microseconds. Yes, and it's longest time. And then in the community, people are trying to reduce this time scale of the measurement, but the way to measure the quantum state of the atom is relying on the spontaneous emission from the atom. I mean, like the fluorescence to the camera through optical path. And the lifetime of the excited state is physically determined. It's a little bit difficult to engineer, but still there's a way, for example, you can make cavity to enhance the fluorescence.
So, but you just measure at the end.
If you make this term quantum computation.
Yes.
So what he said is the
You want to measure?
Right.
yes,
Right.
quantum error correction.
Yes. Okay.
Yes. So one way of thinking is that in the end, the coherence time of the spin qubit is way longer than the measurement time scale, order of seconds. So one way of expansion is that we don't care. Even with the long measurement time, it's okay. But in practical purpose, I think if your error correction is order of kilohertz, it's too long. So you have to do more research through this.
Okay, if there are no,
What happens when you after you have the pulse laser excitation, and if you just leave them alone, like at some point they're going to realize that they are next to each other, right? So will one of them so I was wondering, as you explained, you can actually use pulse laser excitation to have two neighboring Rydberg atoms because of the time scale is so short.
Yeah.
But what happens if you just leave them alone for a while after that, putting them in that state? Well, because then at some time scale, they will have to have the Rydberg atom interaction with the blockade energy, right?
Yes.
So will one of them be forced to go to the ground state, get back to the ground state, or will one physically move in the position, or?
Yeah, so of course after excitation, atoms start to make an interaction, and you can utilize it. And also, if you don't want to make interaction, then you have to bring back to the ground state. There's no way to say, at least it depends on the atomic species. In the case of the rubidium atom, it's impossible to capture Rydberg state of the rubidium and then move it. And if you use another species, then there's a way to capture, but still the time scale of the moving tweezer is longer than the rhythm lifetime. And it's a bit difficult to move around the rhythm. You can move ground state atom.
I was imagining if you could use it to excite all the atoms into the Rydberg state on a square lattice or whatever, and then, you know, if you just let them stay, would it be something similar to an adiabatic situation, like where you adiabatically include the interacting term?
Yeah.
Or so will it be like adiabatic state separation? If you do that?
So you already finished excitation. So
Right.
it's a bit difficult.
It's more like injecting just energy and, okay.
Yeah, okay. Okay, if there are no further questions, let's thank the speaker for a very nice talk.